This video is for my Biology for Health Sciences class. We're still on Unit 2. This is the second video on chemical bonds. Now, you can't understand chemical bonds without understanding the structure of atoms and elements, so please watch my lecture on atoms and elements first before moving into this video. In that video, we talked about how the number of electrons in the outermost shell, called the valence shell, determines the chemical properties of an atom. And we also talked about how the atomic number of an element, which is the same as the number of protons it carries, we talked about how that dictates how many electrons will be in the valence shell. Atoms whose outer shells are not full tend to interact with other atoms in ways that enable them to complete or fill their valence shells. When two atoms with incomplete outer shells interact, each atom will share, donate, or receive electrons so that both partners end up with complete outer shells. These interactions usually result in atoms staying close together, held by attractions called chemical bonds. So in this way, you can see how the elemental identity of an atom is linked to the protons. Ultimately, it's the number of protons that dictate how an atom is going to behave chemically, because the number of electrons it carries dictates how it interacts with other atoms, and it's the protons that dictate how many electrons the atom carries. Now, an ion is an atom or a molecule with an electrical charge resulting from the gain or loss of one or more electrons. When an electron is lost, a positive charge results, because remember, in the nucleus are positively charged protons. Usually they're balanced by the negatively charged electrons orbiting, but if you lose an electron, then you have an imbalance. You have more protons than electrons, so you have a positive charge. Conversely, when an electron is gained, a negative charge results, because now you have more negatively charged electrons than positively charged protons. As we saw in the previous video, sometimes an atom loses electrons to lose an incomplete outer electron shell, leaving it with the complete electron shell that was beneath it. Other atoms might gain electrons to complete an incomplete outer electron shell. This results in an inequality between the protons and electrons carried by that atom. Now, when an atom has a positive or a negative charge because of an imbalance between protons and electrons, we call it an ion. Now, two ions with opposite charges attract each other. When the attraction holds ions together, it is called an ionic bond. Salt is a synonym for an ionic compound, where you have a positively charged ion and a negatively charged ion attracting each other because opposites attract. And remember, a compound is a substance which has a consistent ratio of two or more elements. So we can take the example of table salt. Table salt is a sodium ion and a chlorine ion. The sodium's positively charged, the chlorine's negatively charged, and the opposite attractions pull them together always in a 1-to-1 ratio. All right, let's do a quick review of ionic bonds. So I'm just going to write ionic bonds up here. We introduced this a little bit in the last lecture video. So I'm going to use sodium chloride again, which is table salt. So remember chlorine, so sodium chloride, this is chlorine. That stands for, that's chlorine. Chlorine has an atomic number of 7, so it has, of 17. So it has 17 protons in its nucleus. And then it attracts 17 electrons to orbit it. So let's see how those arrange themselves, right? They have 2 in the inner orbital, and then that inner shell is full. Then we have 8 in the next. 1, 2, 3, 4. They don't pair up unless they have to. 5, 6, 7, 8. So that's 10 total, and the remaining 7 have to go in the third electron shell. So 1, 2, 3, 4, 5, 6, 7. Okay. 1 empty slot, and then its outer valence would be full. So let's do sodium now. Sodium, you might recall, it's a symbol is Na. Don't worry about why. It has an atomic number of 11. That means it has 11 protons in its nucleus, and it attracts 11 electrons. So there's 2 in the inner shell, 8 in the next, for a total of 10, and then 1. The last of those go in the third. Now sodium is missing 7 electrons, and it needs 7 more electrons to fill its outer valence. It could gain 7 electrons, maybe. That'd be kind of difficult because it's only got 11 protons in its nucleus. They're not really going to attract 7 more electrons. It's much easier for sodium to simply lose the outermost electron that's all by itself, and that leaves it with a complete valence shell beneath it. So what tends to happen in this case is this electron will just move over here, right? It'll just take this spot. So let's just erase that outer orbital. This electron from sodium goes over here. Now, chlorine has an extra electron. It has 17 protons and 18 electrons, giving it a net charge of -1. So we say that chlorine is a negatively charged ion. It's an anion. And then sodium has lost an electron. So it has 11 protons, positively charged protons, and only 10 negatively charged electrons. So it has a net charge of +1 because it's got 1 more proton than electron. So it has a net charge of +1, so Na+. Now, this negatively charged chlorine and this positively charged sodium are going to stick together like magnets because opposites attract, remember. So we have this larger chlorine with its 3 electron shells and the smaller sodium with its smaller electron shells, fewer electron shells, and they just stick together like magnets. And that's an ionic bond. So here's a prettier picture of a salt crystal. Salt is a crystal because the sodium and chlorine, they arrange themselves in a repeating pattern. So you see this, the green spheres are the chlorine, the larger green spheres because it has 3 electron shells. And the sodium is the yellow smaller spheres because it only has 2 electron shells. And because of their opposite charges, the positively charged sodium surrounds the negatively charged chlorine, and the negatively charged chlorine surrounds the positively charged sodium. And it ends up settling in together in this matrix, this repeating pattern, which creates a crystal. And again, it's a compound because sodium and chlorine always exist together in table salt in a 1-to-1 ratio. Now, in a covalent bond, 2 atoms, each with an unpaired electron in their outer shell or their valence shell, always share a pair of electrons. Now, what we saw with sodium chloride is that the chlorine completely took an electron from sodium and there was no sharing. And then the opposites attracted to hold the 2 separate atoms together like magnets. But in a covalent bond, it's a little bit different because there are electrons being shared and they circle around the 2 atoms, and it's the shared orbital, the shared electron orbital that holds the 2 atoms together. So 2 or more atoms that are held together by a covalent bond forms a molecule. So a molecule is more than 1 atom, so 2 or more, held together by shared electron orbitals. Let me just sketch out what I mean about these covalent bonds. So covalent bonds is what we're talking about now. Covalent bonds. All right, let's start with hydrogen because hydrogen's easy and we've talked about it before. So remember, hydrogen has an atomic number of 1, and so it has 1 proton in its nucleus. And that 1 proton attracts 1 electron. Okay. But it has 1 empty slot. Now let's talk about making, if 2 of these hydrogens got together, each one with its 1 proton and 1 electron, they could share, right? So each one had 1 empty slot and each one had 1 electron of its own, right? Because each one has 1 proton and 1 electron. So each one came with 1 electron and each one needed 1 more electron to fill that inner electron shell, which takes 2 electrons, remember. So when they get together and they share, they both get to have a full valence, a full electron shell. So the innermost electron shell is full now because the innermost electron shell is full with 2. Together, they each have 2. So these 2 electrons are going to travel around both of these nuclei. And they just like orbit. And remember, electrons, you know, they create a cloud. They're very fast moving. They have these strange quantum mechanic properties. They seem to be in all places of the orbit at once. And so they are holding, their orbit around both of these nuclei is holding the 2 nuclei together. And that is a molecule. It's 2 atoms held together by shared electrons. Their electrons are orbiting both of them, and that holds them together. So one hydrogen isn't taking the electrons, they're actually sharing them equally. So we can draw this. This is the chemical formula for this is H2. And so I want to talk a little bit about these. We've talked about a lot of superscripts, subscript, you know, and subscripts. So remember, if hydrogen, we talked about a superscript that had to do with atomic mass and isotopes before, right? So hydrogen can have 1 proton, or it can have a proton and a neutron. There's a neutron. And I'm using my color coding from the previous lectures, right? So protons are red, neutrons are orange, electrons are blue. So each of these could have the same number of electrons, but one's heavier than the other. So here's the superscript for these atomic masses. One proton creates an atomic mass of 1. So this is hydrogen 1, and this is hydrogen 2. It has an atomic mass of 2. It's a 1 proton plus 1 neutron, and they have approximately the same mass, so it doubles their mass. So that's that superscript. Now, if a hydrogen lost its electron, here we go. Let's just say this hydrogen lost entirely its electron. It's now going to be hydrogen plus, or plus 1, but we could just write plus. So this hydrogen has 1 proton and no electron. Protons are each plus 1, and every electron is a minus 1. So we have a net positive charge, plus 1 charge here. This subscript down here indicates that there's 2 hydrogens stuck together in a molecule. It's a molecule because there's more than one held together by shared electrons. Okay, so H2. We can draw it like this. So this is a notation for molecules so that we can build molecules on the paper and sort of model what they look like. So each line indicates a pair of shared electrons. It's always a pair. So this line represents both of the electrons that are shared between these hydrogens, holding them together. Let's look at another example. Still covalent bonds. Let's look at methane. Methane has a chemical formula of CH4. That means 1 carbon and 4 hydrogens, okay? So that's a 4 there. 1 carbon and 4 hydrogens. And so let's look at carbon. Carbon has an atomic number of 6, so that means it has 6 protons in its nucleus. Okay, so this is carbon. That means it attracts 6 electrons. We're getting good at drawing these orbitals, right? 2 in the innermost shell and 4 more in the next shell. You know what? I didn't leave enough space for this molecule to be built. So I'm just going to have to make this a very small orbital. Okay. And remember, they don't pair up unless they have to. So those 4 are going to all be unpaired. Carbon has 4 empty slots here. That means carbon always makes 4 bonds. The number of empty slots tell you how many covalent bonds a molecule is capable of making. So carbon makes 4 covalent bonds. And so now we have 4 hydrogens. Now remember, each hydrogen has 1 proton and brings with it 1 electron. So let's bring it right there. And it has 1 empty slot that's filled by carbon. So carbon shares one of its unpaired electrons with hydrogen, and hydrogen shares one of its unpaired electrons, its 1 unpaired electron with carbon. And so they each brought an unpaired electron, and those electrons pair up, and now they're shared. And now we do that for each of them. So these are the hydrogens. So this is H. This is an H as well. It has one proton. This is an H as well, and this is an H as well. And so let's bring, each one brings one electron to go with its one proton. And here. Okay. So now if we look at the sharing, how many electrons does each hydrogen have? It needs 2 to fill that innermost electron shell, which is its outer electron shell. So this hydrogen here has 1, 2. This hydrogen here has 1, 2. This hydrogen here has 1, 2. This hydrogen here is 1, 2. Oh, they all have a full valence because of this sharing with carbon, so they're all stable and content. All right, so now the carbon, how many does it have? So 1, 2, 3, 4, 5, 6, 7, 8. Its outermost electron shell has 8 electrons, and since that's the second shell, that's full. So now carbon is full and it's content. So you can see from this how different atoms that have incomplete outer electron shells, incomplete valence shells, can interact with each other in such a way, share electrons with each other in such a way to complete their outer shell. So the way we would draw this is like this. Remember, every single line here connecting the carbon to a hydrogen represents a pair of shared electrons. So this is 2 electrons, 4 electrons, 6 electrons, and 8 electrons. So that's 8 around carbon and 2 for each hydrogen. We don't draw the innermost shell. So those 2 electrons that carbon carries in its innermost electron shell, we ignore those. Only the most superficial shell, the valence shell, matters when you're thinking about how atoms are interacting with each other to form molecules. The inner shells we can just ignore because they're not part of the interaction. They're already full of electrons, so they don't interact with other molecules. All right, let's do another example here with oxygen. I want to talk to you about double covalent bonds. So let's do this. Double covalent bonds. Let's talk about oxygen. Let's talk about atmospheric oxygen, dioxide. Okay, O2, that's 2 oxygens held together with a covalent bond. But this one's a little bit different. So oxygen has an atomic number of 8, meaning it has 8 protons in its nucleus. And we're going to do 2 of these, right? That means each one is going to bring with it 8 electrons. 2 on the inner shell, then 1, 2, 3, 4, 5, 6 in the outer. So that's 8 total. With 2 empty slots, that tells you that oxygen can form 2 covalent bonds. Here, we have the same thing. Another oxygen. 8 protons and 8 electrons to balance them out, which leaves 2 empty slots in the outermost valence shell. So oxygen forms 2 covalent bonds, and it can form both of them with the same molecule or each other. These electrons could pair up, and these electrons could pair up. Oops, this one goes here, this goes here, right? Those could pair up. So how would that look? Okay, let's see. We've got oxygen and oxygen, and I'm going to ignore the inner electrons. Okay, this is going to be hard to draw. So there's 2 pairs of electrons that are not shared, and then there's 2 that are shared. 1, 2, or 2 pairs that are shared. So 4 electrons that are shared, right? 1, 2, 3, 4 that are being shared. So now, again, let's count the electrons. This is the second electron shell. That means it's full with 8 electrons. So now that they're sharing, so each one had 6 and needed 2 more. And now they're sharing. So now what do they have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. That one's full. 1, 2, 3, 4, 5, 6, 7, 8. That one's full because the 4 in the center are being shared between them. So how would we annotate this? We would draw it like this. Okay, so again, each line represents a pair of shared electrons. So 2 lines represents 2 pairs or 4 electrons being shared. We ignore the electrons from inner shells. We only show what's going on with the outer shell, the valence shell. And we could draw here the pairs of electrons that are not shared between the 2. But we don't. I mean, biologists get so lazy, chemists get so lazy because there's just so many electrons to draw all the time. It just gets boring. And they're not really that informative because after a while you'll learn, it'll become intuitive to you that there are these electrons that aren't being shared. So we're just not going to draw them. You could. It's okay to, if you want to, if it helps you keep track. But generally you won't see it. In a book you'll just see the molecule drawn like that. So that's a double covalent bond. You can even have triple covalent bonds. Sometimes there are 2 atoms that are sharing 3 pairs of electrons with each other. Cyanide is a good example. Cyanide has this chemical formula. It's C and N. Nitrogen can form 3 covalent bonds. Carbon forms 4. So 3 of carbon's bonds it forms with nitrogen. So that's a triple covalent bond. And 1 of its bonds it forms with hydrogen. So there's cyanide. Triple covalent bonds, 6 electrons being shared between carbon and nitrogen. All right, so we've covered ionic bonds now, and we've covered covalent bonds. We've covered double covalent bonds. Now, one last bond type for you. I'm going to use oxygen again, and another famous example, water. I want to talk about polar covalent bonds. Polar covalent bonds. H2O. That means 2 hydrogens and 1 oxygen, all in the same molecule, all held together by shared electrons. So this is water. All right. Now, oxygen, I said 8 protons, right? And then we have hydrogen, and we know hydrogen at this point. There's the 1 proton, there's the 1 proton. It's going to be surrounded by 1 electron. Fill the empty slots for oxygen, and oxygen will fill its empty slots. All right, so that's H2O. That part's pretty normal. You would draw it like this, oxygen with a pair with this hydrogen and a pair of shared electrons with this hydrogen, and you could draw these unpaired electrons, the unshared electrons, but we typically don't. We'll just take those away because they're not usually drawn. All right. There's one strange thing about this bond, though, this covalent bond. Oxygen is an electron hog. It has so some elements have just a stronger pull over electrons than others have. So these electrons are spending more time with the oxygen than they are with the hydrogen. So as they're spinning around, they're like spinning mostly around the oxygen and then back again, and then mostly around the oxygen and back again, and then mostly around the oxygen, back again. So they're just spending more time around oxygen than hydrogen. Now, because electrons are negatively charged, that makes the oxygen have a slightly negative charge. It's not a full negative charge the way it would be with an ionic bond, right? Like chlorine just completely took an electron away from sodium and they're not sharing it at all. These electrons do go back to the hydrogen. They just spend more time with the oxygen. And when they're all around the oxygen, it gives the oxygen a negative charge, which then flickers and goes away when the electrons go back to the hydrogen. It's like a flickering negative charge. And meanwhile, conversely, the hydrogens each have a positive charge associated that's also weak and flickering, a partial positive charge we call it. So these are Greek deltas. The Greek delta indicates that this is not a full charge like on an ion, it's a partial charge. And the reason it's there is because oxygen has a stronger attraction to electrons than hydrogen does. So it's an electron hog. You can think of it like a game of tug of war, where, if two individuals are unequally matched in a game of tug of war, the rope starts to move towards them more. Whereas if they're perfectly equally matched, then the rope doesn't move at all. So 2 elements that are sharing electrons that have an equal strength of attraction to those electrons will spend equal time around both of those elements. But in this case, in water, you have an oxygen that has a stronger pull for electrons than hydrogen, so you're going to have a polar covalent bond. Polar just means the two ends are different. Okay, polar means two ends are different. In this case, they're different because one end of the water molecule is negatively charged and the other end is positively charged. Partial negative and partial positive. All right, I said that was the last bond type, but I lied. There's another bond type that's related to polar covalent bonds or caused by them. All right, hydrogen bonds. Hydrogen bonds. So we have all these water molecules, all right? And each water molecule has a polar covalent bond causing one of the elements to be a little bit positively charged and one of the elements in the bond to be a little bit negatively charged. Now the polar property of water makes water very unique, and it's responsible for all of water's life-giving properties. And we'll talk plenty about that in the next lecture video on water chemistry. Now, polar covalent bonds keep water molecules, that's what holds one water molecule together. But it causes these attractions between different water molecules because opposites attract. So the partial positive charges on all the hydrogens are attracted to the partial negative charges on the neighboring oxygens of the neighboring water molecules. So these are the hydrogen bonds. We call them H bonds for short. It's a little bit like a weak ionic bond. Ions are held together by ionic bonds, and that's just attraction between positive and negative forces. This is like that. It's an attraction between positive and negative forces. It's just weaker. So it doesn't take very much energy to break these bonds. It allows water to be liquid at room temperature. And these hydrogen bonds, these are responsible for all of water's life-giving properties. Okay, so again, here's a prettier image of what I was just drawing. You can see the nonpolar covalent bond in hydrogen gas. So hydrogen and hydrogen have equal tug over electrons. They have equal strength in their pull on electrons, so they share those electrons equally. That's going to be a nonpolar covalent bond. You have a double covalent bond with dioxide or atmospheric oxygen. And again, oxygen and oxygen are equal strength in their pull for those electrons, so that's a nonpolar bond as well. Methane, nonpolar, carbon and hydrogen have equal strengths in their attraction for electrons. So methane is built out of nonpolar covalent bonds. And then you have water with its polar covalent bond, where the oxygen is an electron hog and the hydrogens are weak in their attraction for electrons, and so the electrons spend more time around the oxygen, giving oxygen a slightly negative charge and leaving hydrogen with slightly positive charges. So how do you know if two elements will form a polar or a nonpolar covalent bond? How can you know whether they will share their electrons equally or unequally? Well, to figure it out, you'll actually need an electronegativity chart. So what is electronegativity? It's the strength of attraction to electrons. So the more electronegativity an element has, the stronger its attraction for electrons. Less electronegativity, weaker attraction for electrons. And electronegativity is related to the distance between the valence shell and the nucleus. So the farther away that outer shell of electrons is from the positively charged protons, the less those protons can attract those electrons. Also, electronegativity is related to the number of protons in the nucleus. So the more protons there are, the stronger the attraction for electrons. So to figure out if two elements are going to form a polar or a nonpolar covalent bond, you simply have to look at an electronegativity chart and compare their electronegativities to see if they have an equal pull on those electrons or an unequal pull on those electrons. So for example, we looked at methane. Methane is a carbon attached to, sharing electrons with hydrogen. Let me get my little laser pointer. So there's carbon. It has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. It's not perfectly equal, but those electronegativities are similar enough that the electrons are shared fairly evenly. And so hydrocarbons in general, carbon and hydrogen have approximately equal strength. There's not enough of a difference in electronegativity to really notice an inequality, like a collection of negative charge anywhere in that sharing, in that pair. But on the other hand, if you look at oxygen and hydrogen, which, H2O, that's water, oxygen has an electronegativity of 3.5, while hydrogen has an electronegativity of 2.1. That's a bigger dissimilarity. So in that case, you really notice, it really makes a difference in terms of how those electrons are shared. So oxygen has a noticeable negative charge because it's noticeably stronger in its attraction for electrons. So these are color-coded so you can see who's more similar and who's more dissimilar. Now, sometimes there's a gradient actually between nonpolar covalent bonds and ionic bonds. So if the two elements exchanging electrons are really unequal in their electronegativities, then what you're going to get is an ionic bond. So we were looking at table salt, right? Sodium chloride. So look at chlorine. Its electronegativity is 3, and sodium is one of the lowest electronegativities. It's 0.9. So chlorine is one of the highest and sodium is one of the lowest. That's why chlorine doesn't even share unequally. It just fully rips away that electron from sodium because their electronegativities are so dissimilar that sodium just can't keep any pull on those electrons. The difference between oxygen and hydrogen is a little bit less. We have a little bit less difference, but still dissimilar enough to get an unequal sharing, but not a complete thievery of electrons. So here is a nicer image showing hydrogen bonds. So within a water molecule, you have the polar bonds causing the oxygens to be negative and the hydrogens to be positively charged, but opposites attract. So the positive charges on each hydrogen in each water molecule will be attracted to the negative charges on the oxygen of neighboring water molecules, and that causes water molecules to stick together. And these are hydrogen bonds. Hydrogen bonds are like weak ionic bonds holding those water molecules together. And it's because they're weak that water is a liquid at room temperature. Now, if you remove all of the thermal energy from water, if you cool it down, you remove thermal energy, those hydrogen bonds will become stable. And then you get a crystal like salt, but in this case, it's called ice. But just add a little bit of energy and you're going to melt that ice. And what happens when you melt ice and you have liquid water is those hydrogen bonds are breaking and those water molecules are just tumbling all over each other. That's what makes it a liquid. Now, water doesn't only form hydrogen bonds with water molecules. It can form hydrogen bonds with other molecules as well, and that's what causes other molecules to dissolve. So any molecule that has a positive or negative charge will be attracted to water, and water will be attracted to it. So again, let's take table salt as an example. Table salt has all these positive and negative charges. So the positive charges on water will surround the negative charges in the salt, and the negative charges on water will surround the positive charges in the salt. That's going to pull the positively charged sodium apart from the crystal and the negatively charged chlorines away from the crystal. That's why salt falls apart in water, and that's what causes it to dissolve. So sugars dissolve in water as well. They're not ionic, but they are polar. They have partial positive and negative charges all over the molecule. And that, again, causes water to be attracted to the sugar and pull the sugar away from the neighboring sugars and causes, sugar crystals to dissolve in water. So anything that dissolves in water has to be polar or ionic. It has to have some sort of electromagnetic charge that is attracted or attractive to the water molecules. So then take methane. Methane had nonpolar covalent bonds. All of the electrons were evenly spread out around all the protons, causing them all to cancel out. It had a neutral charge. There's nothing that's attractive to water there. So methane does not dissolve in water. Hydrocarbons in general do not dissolve in water. So that's going to be things like fats, things like gasoline. Those are all hydrocarbons, nonpolar covalent bonds. Water's not attracted to it. Water is attracted to other water molecules, like little magnets all sticking together, and they exclude things that they're not attracted to. So that is why oils separate from water.